This is our final lesson in Unit 2. We're looking at two variable inequalities. We have a linear inequality when we have an inequality in two variables whose graph is a region of the coordinate plane that is bounded by a line. The boundary is a line in the coordinate plane that separates the solutions of the inequality from the non-solutions. Points of the line itself may or may not be part of the solution. And the set of points in a coordinate plane that are on one side of the boundary of the graph is called a half plane. We use a test point. That's a point that you pick on one side of the boundary of the graph of a linear inequality. And if the test point makes the inequality true, then all the points on that side of the boundary will be solutions of your inequality. But if the test point makes the inequality false, then all the points on that side of the half plane, on the other side of the half plane, will be your solutions. So let's jump in with a visual representation of those vocabulary terms. Here you can see that I have a boundary, which is a dotted line here. So this is my boundary line. And I have a half plane here and a half plane on the other side of the boundary line. And when you have greater than, we're going to draw a dotted or a dashed boundary line. When you have a greater than sign or a less than sign. But when you have a solid boundary line, you have a greater than equal to or a less than equal to. And here's our boundary. In this case, this would be the solid line. And we have a half plane above and we have a half plane below. Okay? So one thing that you want to know here is if you have a 0, 0 is not on the boundary line, you could use that as a test point. So in either case, you see, I don't have 0, 0 in either case. So I've just made a note of that here. If 0, 0 is not on the boundary line, we're going to use this value as a test point, because if it's true, then you shade that region, and if it's false, you jump the boundary and shade the other portion. Let's move on to some examples for when and how to use and how to shade the half planes. So here's a perfect example. If you notice that 0, 0 is not on the boundary line, and we test that when y is 0, is that greater than -2? And that's true, so this half plane is part of our solution set, and we would want to shade that half plane. This is the true area. And I like to mark that with a big capital S. This is the half plane that is true. And I have a dashed boundary, and I'm true above. Now, another way to think about that, if you think about this as being a sentence here, I want all the y values that are larger. So you can think about it. I want the y values that are above the line. So the y values that are above the line, here the y value is -2. So all the y values that are bigger than the line are going to be up here. And that's another way to think about how to go about shading. So we can say we've got a dashed boundary, right? And on that dashed boundary, we're going to be true y values above the boundary line. And then in this example here, same thing. I've got a dashed boundary line, and I want all the y values that are less than the line. So the dashed boundary would be true below the boundary line. So we can shade below the boundary line, and if you like, you can test 0, 0, and you would see that 0 is not less than -2. And if you like to think about that from a test point of view, 0 is less than -2. That's a false statement. So we want to jump the boundary line and shade over here below the line in the true statement. Then over on this right side, all the y values that are greater than or equal to our boundary line, this is our boundary line, greater than or equal to, so here the y value is 1, and y values that are above 1 would be above the line. So the y values in the half plane that are true would be up here. You could also do that by testing 0, 0, and you would find out that 0 is greater than +1 when you substitute a 0 for x. So our true values, we're going to be true above the boundary line. So we're true above the boundary. And we're true on the boundary. So we're true values on the boundary line. If you substitute 0, 1 here, then 1 for the y, and 0, 1 is greater than or equal to 1. Well, 1 is equal to 1, so our statement is true on the boundary line as well. And then the last one in this section, the y values that are less than or equal to the boundary line will be true when you're below the boundary line and when you're on the boundary line, because we have a solid boundary. So shading that section, we're going to shade below and on the boundary line. And again, I'm going to put a big capital S for this is my solution half plane. This is the half plane that's a solution here. So let's jump into graphing on our own and practicing. We want to graph y is greater than or equal to -2x plus 1. And the first thing you want to do is draw the boundary line, which is the equality. And we're going to draw greater than or equal to, so we're going to draw a solid boundary line in that case. And let's take a look at that. So we want -2x, a slope of -2 is going to go 2 down and 1 to the right, or 2 up and 1 to the left. And you notice that 0, 0, our test point, we could test 0, 0, since 0, 0 is not on the boundary line. And we're going to test that. Is 0, which is my y value, is that greater than or equal to -2 times our x value plus 1? Is that true? So 0 is greater than or equal to 1 is false, which makes that half plane below the line not true. So we want to shade the other half plane. So I want to shade above my boundary line. And you can think of it as this side is false and this side is true. So we're going to shade above the boundary line. And values on the boundary line would be true as well. So you don't want to try a number on the line. In this case, you want to try a different test point. Example 2, you can try that on your own and then come back to check your work. With my work, I see I'm going to have my boundary line is going to be y equals -2x plus 1. And because I have a less than, we're going to make a dotted or dashed boundary line. So 2x plus 1, it's the same graph, just a different behavior of our half plane. So we have a dashed or dotted boundary line. And we already knew that 0, 0 was not on our line, so we're going to test 0, 0 into the equation. Is 0 less than or equal to positive 1? And yes, 0 is less than or equal to 1. So our test point was on the true side of the half plane, and the opposite side was the false portion of the half plane. So you should have shaded below the boundary line, or on the left, lower left of the boundary line. Moving on to example 3, this is a practical application. Tina is going to buy P pounds of pasta salad and C pounds of chicken salad for a party. The pasta salad costs $4 per pound, and the chicken salad costs $6 per pound, and Tina has at most $28 to spend. Let's write and graph an inequality that describes the relationship between the pasta and the chicken. So if I relate that verbally, I would say that I have 4 pasta salads, 4 times pasta, plus 6 times chicken. So this is the cost, and that has to be no more than $28. So she could spend exactly $28, but we've got 4P plus 6C is less than or equal to 28. In solving, we would have 4P is less than or equal to negative 6C plus 28, and dividing by 4, that's negative 3 halves once we reduce that fraction, and 4 divided by 28 is 7. So let's go on our graph here. It's not numbered, and we can number that 1, 2, 3, 4, 5, 6, 7. Let's start here at 7, and we're going to go 3, starting at 7, we're going to go down 3 and right 2, down 3 and right 2, and we want a solid boundary line. So we want to be under, and under would be all the values that are less than. So this would be the section that would work for her. So any combination, and you can try anything you want to do. Let's say we tried 2, 2, or some other value that's inside this shaded region. Tina spends exactly $28 for the chicken and the pasta on the line, and she would spend less than $28 for any combination below. So the line itself is spending exactly $28. But here, if she bought 2 pounds of pasta, 2 pounds of chicken, and 2 pounds of pasta, it would be less than $28. Example 4, we want to graph y greater than or equal to negative 2 times x minus 1 minus 3. So here our vertex is positive 1, negative 3, and the a value is negative 2. So it's an absolute value. We're going to move 2 right and 1 left, or, 2 down and 1 right, or we're going to move 2 down and 1 to the left. So starting at 1, negative 3, our boundary line is greater than equal to, so it's going to be a solid boundary, and our boundary would be y equals negative 2, absolute value of x minus 1 minus 3. And the graph would look like this. So 1, negative 3, whoop. And we're going to test an area. So testing, we could test 0, 0. And if we tested 0, 0, y is 0. And the absolute value of negative 1 is going to be positive 1. And negative 2 times positive 1 is negative 2 minus 3. So 0 is greater than or equal to negative 5. That's true. Our test point is 0, 0. This is true up here. So this area under the graph would be false, and we would shade we would shade above or outside of the absolute value graph. So everything above the graph is going to be true. Everything under the graph would be false. This is our solution set up here. All of this is the solution. Example 5 would be one for you to try. It's a little more difficult. You need to solve for y. So your graph is going to be y is less than negative absolute value of x plus 2 plus 4 after you simplified. Your vertex is negative 2, positive 4. Your boundary is y equals negative x plus 2 plus 4, and it would be dotted boundary since it was less than, and your true statement would be below the graph. So your finished product would look like negative 2, 4, and the slope was 1. So your graph goes dotted across here and dotted or dashed across here. And your test area, your test point could have been 0, 0, and you shaded below. This was the true section under here. Where 0, 0 lived turned out to be a true statement, and your solution was here. This was true down here. For example 6, we're working backwards. You have the graph of the inequality, and you're writing the equation. So looking at the graph, you can tell that your b value is at 1, and your slope looks to be 1/2. So with the b value of 1 and your slope of negative 1/2 and a dashed line, so a dashed boundary means you're dotted and you're shaded below, so you're going to be less than, and your inequality is y less than negative 1/2 x plus 1. On example 7, the hk value for your vertex is located at negative 1, positive 4. You have a solid boundary. You're shaded above the inequality, so that would turn out to be greater than equal. Your a value is negative since the absolute value is reflected across the x-axis. So we have a negative slope of 1, and you can tell that it's 1. So your inequality would be y is greater than or equal to negative 1 times the absolute value of x minus negative 1 plus 4. Okay? Then on example 8, this is our last example. You want to buy your favorite candy bar that cost $1 each, and your favorite pepperoni snack that cost $1.50 each. You have $4.50 to spend. Can you write an inequality to represent the situation where C is the number of candy bars you buy and P is the number of pepperoni snacks? So can you handle that? The candy costs $1 times C plus $1.50 times P, and you have $4.50 to spend. So it's less than or equal to $4.50. And solving for P, you should get negative 2/3 candy plus 3. So if we go every other line is an integer, we could come up here for 3, and every other line here could be an integer. And then starting at 3, we're going to go 2 down and 3 to the right, 2 down and 3 to the right, 2 down and 3 to the right. So we end up at $4.50 right there with a solid boundary line. So everything on the boundary line is exactly right. And let's see what they're saying. Why did the graph in B only include quadrant 1? Well, first we need to shade, right? So let's shade. This would be everything under here. And why did the graph include quadrant 1? Well, to me, it's not reasonable to have negative money or negative items. Not reasonable. That wouldn't make any sense. And can you buy 3 candy bars and 2 pepperoni snacks? Explain. So if you think about using that, that's a hint to test. This is our test point, 3, 2. And if you realize from the algebra, 3 candy bars and 2 pepperoni snacks, that's $3. 3 times $1 for a candy bar, and $1.50 times 2 for pepperoni, that's $6. And your budget was $4, but your budget is $4.50. So you can't spend and be in the solution set. And there we are at the end of chapter 2.